Hello everyone. Hope you are doing very well. As you all know that today we are going to see the theory part of the chemical kinetics, and today is the part 4. So let's start with our today's topic, that is NCERT chapter 3 chemical kinetics theory part 4, and we are going to cover the NCERT section 3.3.1 to 3.3.2 in the today's lecture. So let's start. Disclaimer: the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of original creators and owners. If you are the owner and have any concern or issue, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that uh, parts of the content may have been generated using generative AI, so which is experimental. Let's begin with today's objective, which is after attending this lecture, you will be able to derive the integrated rate equations for the zero and first order reactions. And the topics that we are going to cover as per the NCERT are the first one, which is the subsection of the section 3.3, that is 3.3.1, and it is zero order reactions. In this, we will talk about the integrated rate law, derivation of zero order reaction, zero order graph. We also look at the example of zero order reactions. Then we will switch to the second subsection, which is 3.3.2, which is first order reactions. In this, we will talk about the derivation of integrated first rate law, a plot between the ln r and t, plot of log r naught by r versus time, and gas phase first order reactions. And then we will see the examples of first order reaction. And lastly, we will cover some examples from 3.5 to 3.6. So let's begin. So the first subsection or the first topic is zero order reaction. In this, zero order reaction means that the rate of the reaction is proportional to zero power of concentration of reactant. So until now, if you know, we have been covered about the rate law and the rate of the reactions and the rate expression, and we have talked about the order of the reactions and the unit of rate constant, how can you derive that, and what are the factors that are going to affect the rate of the reaction. These are the all major topics that we have covered. Today the first type of order of reaction which we are going to study about is zero order reaction. So until now, if you know, the rate law was defined that the rate will be directly proportional to the concentration of the reactant, to the power of which the stoichiometric coefficient may or may not be present in the reaction, in the balanced chemical reaction. Right, so that was the rate law we have defined. Now, the zero order reaction, as the name says, zero. So, zero order reaction means that rate of reaction is proportional to zero power of the concentration of reactant, right? So whatever will go in the power of the concentration of reactant, that will determine the order, kind of, right? So if you put the power to be zero, then you can say that zero order reaction means that rate of the reaction is proportional to zero power of concentration of reactants. Now let's consider the reaction R converting to P, where R is representing the reactants and the P is representing the product. Okay, one thing I want to say or I want to mention that please, if you have any doubt in between the lecture regarding any topic which we are covering today, kindly ask that in the chat box. You can ask that and we will try to clarify it. So coming back to the point, let's consider this reaction in which the reactant is converting to the products. So the rate for this reaction will be defined as minus of dr by dt, where dr by dt is representing the rate of change of reactant concentration in t time, right? So dr by dt is equals to k times the concentration of the reactant to the power 0. What we are saying, that rate is equals to minus dr by dt, that means rate of change of reactant. This is defined as k multiplied by the reactant concentration to the power 0. K is a reaction constant. Okay, so this is a graph basically which is representing the rate versus the R graph. Okay, rate is representing on the y-axis and the R, that is the R concentration, the reactant concentration, is representing on the x-axis. And as you can see, that graph is a straight line, right? Graph is a straight line. That means as the reactant concentration is increasing, the rate is constant. The rate is having a constant value over the change of the reaction or reactant concentration, right? So this is the figure of plot of rate versus R for the zero order reaction. Okay, so as I said, that rate for the zero order reaction is k times R to the power 0, and if something you put in the power 0, something has 0 power, that means its value will be equals to 1, right? That's the basic thing. So R to the power 0 means it is 1, so rate will become equals to k, right? That means a constant value, rate constant value. So rate is having a constant value if you are changing the reactant concentration or not. That is the representation of rate versus R for a zero order reaction. Now, integrated rate law derivation of the zero order reaction. So the for the zero order reactions, the rate is defined as minus dr by dt is equals to k times R to the power 0. We just have seen, right? For zero order reaction, we consider the rate as k times R to the power 0. Rate can also be written as dr by dt, which is representing the change of concentration of R with the time t. Okay, and we are putting the negative sign because the concentration of R, the concentration of reactant, is decreasing as the reaction is proceeding, right? Because the product concentration is increasing and reactant concentration is decreasing during the reaction. That's why we are putting here as negative. As any quantity raised to the power 0 is unity, as I said that if any quantity has a power 0, what does that represent? That its value is unity, its value is 1. So rate will become minus dr by dt is equals to k times 1, because R to the power will be 1. So rate will become equals to k times 1. That means dr is equals to minus of k dt. You can write it like that, right? After just interchanging the terms, you can write that the change of the concentration of the reactant is equals to minus of k, that is rate constant, multiplied by dt. Okay, this is, you understand. Now dr, we just have said that dr is minus of k dt, right? Now if you integrate the both sides, as we are talking or as we are discussing under the topic integrated rate law derivation of zero order reaction, that means we have to do the integration. So when you are integrating the both sides, now if you have seen or if you have studying the integration part in the mathematics, you have seen that we take the integration only when we have the something changing term at the both side. Like here in this equation, the dr is representing a little change in the reactant concentration which is present at the left hand side, and dt is representing a little change in the time at the right hand side. in this equation, right? That means both side of the equation have some changing thing, changing term, changing quantity, right? Only that in case we take integration. Other than that, if you take the integration of any constant term like k, if you take the integration of constant, that will going to be that constant. Okay, so integrating both sides, when you integrate the both sides of this equation, the integration of dr, that is a little change in r, will become r, because a little change in the r, that means a little part of the r. Dr is representing a little part of the r, or you can say r2 minus r1, which is a little part of the whole reactant, right? When you integrate all those little parts together, it will constitute to a whole reactant concentration. Integration means addition. Okay, you are adding the a little quantity. So dr is representing a small change, that is r2 minus r1. That small change plus the another small change plus the another small change, when you integrate the both dr, integrate the whole dr, we get a whole reactant concentration. So reactant concentration is equals to minus of, when you take the integration of k dt, it will be kt, because the k dt will become, now k is a constant. When you take the integration of k multiply by dt, the k is a constant, so it will come outside of the integration and dt will remain in the integration. Now the change of the little change in the time, when you integrate a little change in the time, similarly here also we add up all the little time together, and they will constitute a whole time, that is t. Okay, and k is constant, so we write the k as it is, plus I is a extra term which can be there if you are adding everything together. So we are just supposing, or we just supposed that I is some amount which is a constant, of course, which is integer, and it could be anything because we are adding everything, so it can be anything other than these other quantities r and kt. So we are also putting negative sign here because we just have seen the rate equation where minus dr by dt is equals to k, right? We just have seen that rate is representing as minus dr by dt. That means the reactant concentration is changing with the time, is equals to k, that is the rate constant, multiply by the concentration of the reactant, right? So why we are putting negative sign? Because we are taking here the concentration of reactant, and in the reaction, reactant converting to product, the reactant concentration is decreasing. Meanwhile, at the same time, the product concentration is increasing. Because the reactant concentration is decreasing, that's why we are taking negative here. The negative is representing that the reactant concentration is decreasing with the time. Okay, so that's why we have the integrated equation as rate of concentration of reactant is equals to minus of kt plus I. Okay, this is representing a ncrt equation 3.5. Now what is I, what represents I, we will see this. So I is a constant of integration. We call this I as constant of integration. What I said that we are integrating, that means we are adding a small quantities from both the sides. So when you adding the small quantities of the reactants, it becomes the whole reactant concentration, and when you add the small time to get the whole time, it become minus of kt. We add a plus I, which is called as constant of integration. Now I hold a integer value which is anything. Okay, which can be anything. So we are adding I just because we don't miss any other value if we are getting after the integration, because everything here is a variable, not a particular quantity or not a particular number. So we are just adding I just in case we are missing anything after addition of everything. Okay, whole time, because the dt is a small change in the time, right? So when you are adding every small change, that means every small fraction of time you are getting a whole time. Whole time means from 0 to t, from t is equals to 0 to t is equals to t, you get t, right, for that time. So that's why we get this equation. This is also an ncrt equation marked as 3.5. You can check out that in our ncrt textbook. And I here is representing the constant of integration. Now at time is equals to 0, the concentration of reactant R is R naught, okay, which is the initial concentration. Because anything if we want to consider as initial, or standard, we put a naught in the subscript of that, right? So if you talk about at time equals to 0, where the reaction is starting or not started yet, then the concentration of reactant is R naught we are considering, which is the highest concentration in the whole time of the reaction. Okay, so at time equals to 0, reactant concentration is R naught, where R naught is initial concentration of the reactant. Now substituting the R naught in the equation 3.5, that is this. So when you put t equals to 0, R will become R naught. You have to put this in equation 3.5. And we are getting R naught is equals to minus of k multiplied by 0, t is equals to 0 plus I. This will become R naught is equals to I. This minus k times 0, that means this whole quantity will become 0 and R naught will become equals to I. Now substituting the value of I in the equation 3.5. Now, okay, so first of all, if you have studied the integration in the mathematics, we put this I after the integration part. Okay, we also somewhere in some books we represent this I as small c or capital C. Okay, that which represents some constant value which we are getting in the integration part. Okay, and then when you solve that equation, where you are getting the c, that is I or I. Okay, when you solve this equation for getting the value of I, that what exactly I is. So here at the time t equals to 0, we are getting that I is equals to R naught. I is equals to the initial concentration of the reactant. Now use this I value to put into the reaction 3.5 to eliminate this constant term which we don't know. Now the R is equals to minus KT plus R naught, right? You put the I value at the place of in the equation 3.5. So this equation will become R is equals to minus of KT plus R naught. Okay, here I was present. We just put I is equals to R naught. So this will be the equation we get, and this is equation NCRT equation marked as 3.6. Now comparing the 3.6 equation with the equation of a straight line, which is y is equals to mx plus c. This also you have studied in the mathematics in the straight lines, that when you compare, what you have to do, you have to compare the 3.6 equation with the straight line equation y equals to mx plus c. And if we plot a graph of r, that is concentration of r, against the time, we get a straight line. Figure 3.3 is also that plot with the slope of minus k and intercept equals to r naught. So this is the figure 3.3, where we are plotting the graph between the concentration of the reactant and the time. So if you can see, we have the highest concentration of reactant at time equals to 0, which is r naught, right? Here we are here you can see we have marked r naught value, which is this value of at the y-axis of the concentration of r, which is the highest one. And as the time increase, the concentration of the reactant will decrease with the time, and the slope we are getting for this straight line is minus of slope. K is equals to minus of slope, or you can write it as slope is equals to minus k. Why negative? Because it is a negative graph, decreasing graph has a negative slope. Okay, so when you compare this 3.6 equation with y is equals to mx plus c, where y is concentration of reactant, so which is this r, x is time, so this is t, right? So that means m is minus k slope, and c, that is intercept, is r naught. So this whole intercept at the y-axis is r naught. That's the highest value of reactant at initial at t equals to 0, and with the increase of time, this is a straight line which we are getting, which is a decreasing graph, and the slope will be minus k. So variation in the concentration versus the time plot for a zero order reaction. Further simplifying the equation 3.6, we get the rate constant K. Now, if you further simplify this equation, you can also get the rate constant value, which is K. So, K is equals to, when you derive or when you simplify this to get the equation of the rate constant, you get the K is equals to, so this R naught will go here in the negative, R minus R naught, and T will go in the denominator divided by T. Now, this minus, if you take here and multiply inside the whole equation, this will become R naught minus R by T. Okay, so from the equation 3.6, we get the rate constant value, which is coming out as initial rate concentration, initial reactant concentration minus the final reactant concentration divided by the time T. This equation is representing the NCERT equation marked as 3.7. Okay, there is no 4O, there is R naught. Okay, there is R naught, which is representing the initial concentration of the reactant from the reaction at time T is equals to 0, and with time the concentration of reaction or the concentration of reactant is decreasing. It is what this graph is showing. Now let's see the example of zero order reaction. So zero order reactions are relatively uncommon, but they occur under special conditions. As it is a zero order reaction, so they are relatively uncommon. You cannot find it commonly everywhere or relatively anywhere, but they occur under special conditions. Some enzyme catalyzed reactions and the reactions which occur on metal surfaces are a few examples of zero order reactions. If you talk about enzyme catalyzed reactions, what are enzyme catalyzed reactions? You can observe these type of reactions in the biology and the chemistry also, where there is an enzyme which needs catalyst to catalyze the reaction, and the reaction is happening properly or rapidly to increase the rate of the reaction. Okay, so enzyme catalyzed reactions and also the reactions which happens at metal surfaces, right, like rusting of iron, in which iron is undergoing the oxidation process, right? These type of reactions are the few examples of zero order reactions. Decomposition of gaseous ammonia NH3 on a hot platinum surface is a zero order reaction at high pressure. Okay, there is also a condition that it is occurring at high pressure. Decomposition means the dissociation, or you can say breaking down in the constituent elements. So decomposition of gaseous ammonia on a hot platinum surface, it is also a zero order type of reaction at high pressure. It needs high pressure to occur. This is the reaction. 2NH3, two molecules of NH3 at the 1130 Kelvin, the high temperature, and platinum catalyst present, it is dissociating or decomposing into the nitrogen gas and 3 molecules of H2, that is hydrogen gas. Okay, so this is a decomposition of ammonia on a hot platinum surface, which is acting as a catalyst here, platinum, and also it is undergoing at the high pressure and temperature. This is a zero order reaction example. Rate for this reaction is K times the concentration of the reactant to the power 0. Right? Because for the zero order reaction, the power will be having the 0 value for the concentration of reactant, and hence the rate will be equals to the rate constant, that is K. Now in this reaction, platinum metal is acting as a catalyst. As I said, platinum is acting or serving as a catalyst in the decomposition of ammonia. Now at high pressure, the metal surface gets saturated with the gas molecule. Okay, so at high pressure, the metal surface at which the reactions happens get saturated with the gas molecules. They will react with the gas molecules, because at the high pressure you are relating, or you are interacting the metal surface with the gaseous molecules. Further change in the reaction conditions is unable to alter the amount of ammonia on the surface of the catalyst, making the rate of the reaction independent of its concentration. Okay, try to understand this, that if you further change in the reaction, if you change the catalyst, if you change the conditions, it is unable to alter the amount of ammonia on the surface of the catalyst, which is making the rate of reaction independent of its concentration. Okay, so whatever the amount of ammonia which we are getting at the catalyst surface to convert to the product, that is not going to affect after if you change the reaction conditions. That means the rate of reaction will become independent of the concentration. Okay, so no, it is not necessary that zero order always contain catalyst. This is may or may not be true, because catalyst just used to increase the rate of the reaction, and catalyst is a special condition. It comes, or it is one of the way, or it is one of the options which comes under the special conditions for happening of a zero order reactions. Other can be high pressure, high temperature, or the special conditions which you have to provide to happening of a reaction, for taking place of a reaction. Okay, and as this point clarify that if you further change in the reaction conditions and think that reaction will happen more rapidly or rate of reaction increase, this is not going to happen, because if you change the further condition, it is unable to alter or to convert amount of ammonia, or to change the amount of ammonia present on the surface of the catalyst for getting the product, which makes the rate of reaction independent of the concentration. Thermal decomposition of hydrogen iodide on the gold surface is another example of zero order reaction. This is another example where the thermal decomposition of the hydrogen iodide molecule on the gold surface is an example. Now let's switch to our next subsection, which is 3.3.2 first order reactions. Now in the first order reaction, the rate of the reaction is proportional to first power of concentration of reactant. As the name says, first, that means the in the power of the concentration of reactant there will be 1. Okay, so this is the definition, similarly saying that rate of reaction is proportional to first power of concentration of reactant R. If you consider again a reaction where the reactant is converting to the product, the rate is defined as minus of dr by dt. That means the change of concentration of reactant with time is equals to k times the reactant concentration to the power 1. Right? If power has 1, we don't have to put it right here and write 1, because if r is written, that means in the power it has already contained 1. Okay, so minus dr by dt is equals to kr. K is a rate constant. Minus sign, I hope you all understood now that minus sign, because we are talking about the change of concentration of reactant, and the concentration of reactant is decreasing with the time, and that is what this negative sign is indicating. So we can also write it as dr by r, this r we can put here, is equals to minus of k dt. So we take the same variable at the same side and the another variable at the another side. And this is the graph of rate and the concentration of the reactant, and this is a straight line or increasing graph. So this is a plot of rate versus the r of t, that is the reactant concentration at time t for the first order reaction. Okay, so that's, you can see that they are proportional, directly proportional. As the concentration of the reactant with the time increasing, the rate is also increasing proportionally. Now let's see the derivation of integrating first rate law. So dr by r is equals to minus k dt. This is the expression we just simplify, right? Because minus of dr by dt is equals to k of r. So we take the same variables at the same side. So dr by r is equals to minus of k dt. Now when you integrate this equation at the both side, we will get ln r is equals to minus kt plus I. Now where this ln r came? So this is a rule. If you want to mention, you can write it somewhere, or if you know the mathematics integration, then you know the formula, that integration of dx by x, or here integration of dr by r, is equals to the ln r, ln x. Okay, this is the formula for the integration. So integrating, when you integrate the left hand side of this equation, it will be ln of r is equals to, when you integrate the right hand side, it will be minus of kt plus I. K is a constant, so we put it outside of the integration sign, and dt integration will be t, and we add some extra amount which is plus I, which is a constant of integration, as I explained. So this is the equation you get after the integration of the rate law or first rate law. This equation is marked as NCERT equation 3.8. I is the constant of integration and its value can be determined easily. So again, the similar thing, that when t is equals to 0 at the 0 initial time, the r will be r naught, where r naught is representing initial concentration of the reactant. Therefore, the equation 3.8, that is this equation, can be written as ln r naught, r will become r naught. So ln r naught is equals to minus k multiplied by 0, because t we are taking 0, plus I. From here, I will become equals to ln of r naught. So we get the value of I, right, which is a variable. I is a variable, but we get the value of I, which is ln r naught. Now we have to put this in this equation 3.8, similarly which we have done in the case of zero order reaction. So ln r naught will become equals to I. Okay. Now substituting the value of I in the equation 3.8. 3.8 equation was ln r equals to minus of kt plus I. Now when you put this I here, the ln r will become equals to minus of kt plus ln of r naught. We just have put the I value we derived in this equation, and we get this equation as NCERT equation 3.9. ln r is equals to minus kt plus ln of r naught. Now rearranging this equation to get the value of k, ln r by r naught, because this ln r naught will go here in the left hand side, so it will become ln r minus ln r naught. When two ln values are in negative or subtraction, you can write it as ln of the first equation, first quantity divided by second quantity. Okay, so ln r minus ln r naught will become ln r by r naught is equals to, here minus kt will remain, and from this k value will be 1 by t of ln r naught by r. So we take this negative sign, it will go in the multiplication of ln r by r naught. This multiplication of minus 1 with the ln will go at the power of the r by r naught, which rearrange the numerator and the denominator, and that's why we got r naught by r. This is also a property of log, that if log if the ln value has something in the power, it can go in the product with the ln, and similarly if it is having something in the uh, it is having something in the product, then it will go in the power of the value of ln. So here this minus will go here in the product, and from the product it will go in the power of r by r naught, and this power when you take inside, the r naught and r will change in their places, and r by r naught will become r naught by r. Okay, so k value, that is rate constant value, finally become 1 by t of ln of r naught by r. This is ln, which is the representation of logarithmic term. Okay, so this k value, rate constant value, is a NCERT equation marked as 3.10. At time t1, from the equation 3.8, which is ln of r minus kt plus I, the ln of r1 is equals to minus of kt1 plus ln of r0. Okay, so ln is basically logarithmic term and it has different values, like ln1 is something, ln2 has some value, ln3 has some value in decimal. Okay, so it has some numeric thing. So we are saying here that at time t1, initially we have taken t equals to 0, and if you take time t at 1, that means at some second. Okay, so we are considering that as time t1. So at some point of time t1, this equation will become ln of the concentration of reactant at 1, that is at that point, is equals to minus of k of t1 plus ln of r0. Ln r0 will not change because it is the initial concentration of reactant. This equation is representing the NCERT equation 3.11. Now similarly at time t2, the equation will become ln of r2 is equals to minus of kt2 plus ln of r0. This equation is representing the NCERT equation 3.12. Now here r1 concentration and r2 concentration are concentration of reactants at the time t1 and t2 respectively. Now we have to subtract the 3.12 equation, that is this equation, from 3.11. So you will get ln of r1 minus ln of r2 is equals to minus of kt1 minus of kt2. We just have to subtract these two equations. And you will get ln of r1 by r2 is equals to k times t2 minus t1. This is the equation you will get after subtraction. And you can rearrange it to get the value of rate constant, which is 1 by t2 minus t1 ln r1 by r2. This is the value for the rate constant for any t1 or t2 time. This is representing the NCERT equation 3.13. Now equation 3.9 can also be written as, equation 3.9 is this one. So this can also be written as ln r by r0 is equals to minus of kt. Right, this can be written as like this because this ln r0 will go here in the subtraction, and ln r minus ln r0 will be ln r by r0. This is a property of logarithm, is equals to minus of kt. Now taking anti-log of both sides. Now this is in the log term. Now if you take the anti-log at the both sides, it will become r is equals to r0 e to the power minus kt. What we have done, basically ln has here base e. If you talk about log, log has base 10. ln has base e here. E somewhere here at the base is written. So what will happen? This quantity, when you remove the ln at the left hand side, this quantity will become equals to e to the power minus of kt. Okay, so this base e will go at the right hand side, and whatever is quantity present at right hand side, that will go in the power of the e or power of the base. Okay, so base is e, so this quantity r by r0 is equals to e to the power minus of kt, and you can also write that as r is equals to r0 e to the power minus kt. Okay, so this is the equation marked as NCERT equation 3.14. First order rate equation, which is marked as 3.10, which was k is equals to 1 by t ln r0 by r, can also be written in the form of k is equals to 2.303 by t log r0 by r. Now if you see, here we are talking about ln, here we are talking about log. Both are a little different. If you want to convert the ln base e to log base 10, you have to multiply the ln term with 2.303, and it will automatically get converted to the log base 10. Okay, so you can write this 3.10 equation of first order rate equation as k is equals to 2.303 by t for the ln conversion to log, and log r0 by r. Rest will remain same. This equation is marked as NCERT equation 3.15. And from here, log of r naught by r is equals to kt upon 2.303. This is just a rearrangement of this equation. Now let's see the plot between the ln of rate, ln of reactant concentration and time t. So comparing the equation 3.9, that is this, ln r equals to minus kt plus ln r naught, with y is equals to mx plus c. If we plot the ln of r against the time, which is marked as figure 3.4, we get a straight line and slope minus k and intercept equals to ln of r naught. So this will be the plot where you can see that we are plotting the ln of r versus time graph, where we are getting the straight line, right, which is a decreasing straight line. So that's why the slope is negative minus k. And at t equals to 0, the ln of r has highest value ln of r naught at the initial time. Okay, so this is showing a plot between the ln r and t for a first order reaction, and this is marked as figure 3.4. Now plot of log of r naught by r versus time. So if we plot a graph between the log of r naught by r versus the time, which is marked as figure 3.5, slope will come out as k upon 2.303. So this is the graph between log of r naught by r versus time. The slope is a straight line, increasing straight line having positive slope k upon 2.303. Okay, so this is marked as figure 3.5, the plot of r naught by r versus time for a first order reaction. Okay, so at time t is equals to 0, we are taking the values for the log of r naught by r, or either the rate or either the reactant concentration value. We are considering the t value as 0 in different equations to get the value of I, the constant of integration, to put it into the main equation so that we can get the value of rate constant k. Okay, that's why we are again putting t is equals to 0. And in the graphs also, we are comparing the t equals to 0 value, that at t equals to 0, what is the reactant concentration value, which will be the initial value, that is r naught, which is the highest concentration of reactant overall during the overall of the reaction, right? Gas phase first order reaction. Now let's see what is gas phase first order reaction. Let us consider a typical first order gas phase reaction. So this is a gas phase reaction where every element or every reactant and product are in the gaseous forms, A converting to B plus C. Now let Pi representing the initial pressure of A and Pt is the total pressure at some time t. Integrating rate equation for such a reaction can be derived as total pressure, that is Pt, will be equals to Pa plus Pb plus Pc, which is pressure units for the reactant and the product. So this is a table representing the reaction A converting to B plus C, and at time equals to t, what is the pressure, and at time t equals to t, what is the pressure. So at time t equals to 0, the A pressure is Pi, initial pressure. Meanwhile, the B and the C pressures are 0 atmosphere because the reaction hasn't started now yet. Okay, but after reaction started and we just stop or look out at time t, so at time t, the A pressure is Pi minus X. So some amount of pressure decreases, Pi minus X atmosphere. Meanwhile, whatever the amount of X decreases, that will be the amount of B and C pressure, that is X atmosphere for B and X atmosphere for C. Pi is representing the initial pressure at the time 0. Now P total will be whatever the pressure will be at time t, that will be the P total, which is Pi minus X of A plus X of B plus X atmosphere for C. When you add them, 1x will cancel out, the remaining term will be Pi plus X. This is the total pressure at some time t for the reaction. So from there, x value will be P total minus P initial, where the PA is representing the P initial minus x term, right? The pressure of A, the pressure of reactant, is Pi minus x, right? So it will become Pi minus x. X is Pt minus Pi, so we put inside. So Pi minus Pt minus Pi. This minus when go inside, it will become Pi minus Pt minus minus plus Pi. So Pi will be 2Pi. So it will be 2Pi minus Pt. Okay, so we find out the x value, that what is the amount of pressure that is decreasing for the A reactant and that is increasing for B and C reactant, B and C product at some time t. So we get the value of x as P total minus P initial. Then we have the pressure at time t of A as Pi minus x. So we put the value of x we derived here, and then we can finally find out the pressure of A, that is 2P initial minus P total. So K is given as 2.303 by T log of Pi upon Pa, that is P initial upon the pressure of the A reactant. This is NCERT equation 3.16. And you can also write it as 2.303 by T log of P initial will be P initial upon, there should be P final, right? And PA is coming out as 2Pi minus Pt. So 2Pi minus Pt. In the terms of the pressure of the A, we have written the rate constant value. Okay. Now examples of first order reaction, and we are seeing the example 3.5. So hydrogenation of ethene is an example of first order reaction. Okay, so what are the examples of first order reaction? So hydrogenation of ethene. Ethene is an unsaturated compound. If you remember, ethene representing that ethene has 2 carbon in it, right? Both are bonded with double bond between them. When you do the hydrogenation of ethene to get the ethane, so this process is an example of first order reaction, which is C2H4 adding H2 into it and getting C2H6, which is ethane. So this is a example of first order reaction. The rate for this order is K times C2H4 to the power 1. Okay, which is representing a first order rate. All natural and artificial radioactive decay of unstable nuclei take place by first order kinetics. So any radioactive decay which is happening naturally or artificially for a unstable nuclei, they also happen by first order kinetics or first order reaction. So like radium having the mass 226 with the electrons 88, it is decaying into the helium having mass 4 electrons 2 plus Rn having the mass 222 and the electrons 86. So this is a decay of radium, and radium is an unstable nuclei, a decay radioactive product or radioactive element, and this reaction is taking place by first order kinetics. Rate for this reaction is K times rate constant times the concentration of reactant, that is radium. Decomposition of N2O5 and N2O are some more examples of first order reactions. Okay, so these are also the example of first order reactions. Decomposition of the N2O5 and N2O. So let's see the example, which is marked as 3.5 as per the NCERT textbook. Example is saying that initial concentration of N2O5 in the following first order reaction, which is N2O5 converting to 2NO2 plus half of O2. The initial concentration of N2O5 was 1.24 times 10 to the power minus 2 mole liter inverse at 318 Kelvin. the concentration of N2O5 after the 60 minutes was 0.20 times 10 to the power minus 2 mole per liter. Now calculate the rate constant of the reaction at 318 Kelvin. So this is the example that you have to tell about the rate constant of the reaction, where the initial concentration of N2O5 is given and the reaction is also given following the first order reaction. So you have given some time. Try to just analyze and solve it. We will see then what is the correct answer. Okay, let's see. So for this given example, first of all, we know that for a first order reaction, the log of R1 by R2, if we have given the two concentrations at two different time, then we use this equation, that is log of R1 by R2 is equals to K times T2 minus T1 upon 2.303. So K from here will be 2.303 divided by T2 minus T1 log of R1 by R2. Now we have the two times given, which is 60 minutes and 0 minutes, because at initial concentration the time is 0, and at final concentration that you have given the concentration of N2O5 after 60 minutes. So 60 minutes is T2, T1 is 0 minutes, 2.303 log of R1, the concentration of the reactant at 0 minutes is given as 1.24 times 10 to the power minus 2 mole per liter, divided by after 60 minutes the concentration is 0.20 times 10 to the power minus 2 mole per liter. This is also given. You just have to solve this, because in this equation only the variable is K, rate constant, and that is what you have to find out. So when you solve out this, it will be 2.303 by 60 log of 6.2 minute inverse, and the K is coming out as 0.0304 minute inverse. Okay, so this is how you can solve this question and get the answer and get the value of the rate constant of the reaction. And this is how whatever we have seen, you can apply that in the questions. Try to solve as many as questions as you want, and try to remember these different formulas of first order reactions and the zero order reactions in different cases for finding out the rate constant value. And if, like in this example, if at two different time we have given the concentrations, then how can you solve that? So we have also derived for that the formula for the first order reactions, which we have used in this example. So this is how you can learn the formulas we have studied in the today's lecture, and you can do the calculation. Okay, thank you so much for joining this session. That is all for today's chemistry session.